I have many bushes at my home, but I am especially fond of 4 of them, so I will define my population as follows. The population consists of the heights of the 4 bushes of which I am especially fond. The heights are 2 feet, 4 feet, 6 feet, and 8 feet. A sampling distribution is the distribution of a sample statistic. The sample statistic I am interested in is the mean height of my bushes taken 2 at a time. This can be done in various ways. One way is with replacement, in which I choose one of my bushes, and then when choosing a second bush, the first bush is available to be chosen again. With this method, the sample 2-4 is different from 4-2. In other words, order is important. The method I will use today, though, will be to consider all the samples of size 2 in which order does not matter. In other words, the sample 2-4 and 4-2 are the same sample because order does not matter. Now that we have generated our sample means, we will associate each mean with its appropriate probability. To do this, we will use the classical approach to probability, in which each outcome, in this case our sample means, has an equally likely chance of occurring. But before we assign our probabilities, let's take a look at what a histogram of the original population looks like. Now let's place a histogram of the sampling distribution of x bar directly above the histogram of the original population and make a comparison. The first thing I notice is that we are building a mound. This is most exciting. In fact, I often tell my students this is the most exciting thing we have done all semester. This mound building will always occur regardless of the shape of the original population. Students often have a difficult time understanding this intuitively. To help understand this important concept intuitively, let's consider the following. Suppose we take 2 of the observations from our original population. Let's take 2 and 4. The mean of 2 and 4, in other words x bar, is 3. We can see how now, instead of having a 2 in the x bar distribution, that we now have a 3. We are moving towards the center. So as our x bars move toward the center, they start piling on top of one another. This results in the building of a mound. This will soon be very important for us in this course. Let's see what would happen if we used a more complex distribution. Let's take a beta distribution. We don't study beta distributions in this course, but a beta distribution with certain parameters looks just like a bathtub. In other words, sunken in the center. But still, we will notice that the sampling distribution of x bar is mound-shaped when the sample size is large enough. Now let's return to our sample means so that we can associate them with their appropriate probabilities. As mentioned previously, we will use the classical approach to probability, in which each outcome has an equally likely chance of occurring. Note that our sample means are 3, 4, 5, 5, 6, and 7. Since we have 6 xbars and there is an equally likely chance of each occurring, we will assign the probability of 1/6 to each of them. But now notice that we have 2 xbars that are the same, 5 and 5. We really only need to list 5 one time. I like to say, let's telescope it, like sliding a telescope together. All we do is list 5 only one time and add the probabilities together. Notice that either way, the probabilities add up to 1. We now have the sampling distribution of x bar for sample size equals 2 in tabular form. We can also put it in the form of a histogram.